Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Rustan Leino, thanks for coming to this session on using verification tools in teaching. I'm joined up here by two educators, Rajeev Joshi and Rosemary Monahan, and I do research on the verification tool sides, but I don't teach, so usually at least. So I have two experts to back me up there. So what we're going to show you is some ways that you could use verification tools in teaching, and then we're going to have some discussion about how we could pool together to share teaching material and such things. But let me get started right away. So what I'm going to do is I'm going to show you one tool, one verification tool called Daphne. So Daphne is a programming language and a verifier, and I'm going to be talking about it. Rajeev has also used Daphne, and then Rosemary is going to talk about another teaching experience using another tool called Spec. Okay, so for the setting, any computer scientist who deals with a program has to, at some level, reason about what those programs do. That is, when you write the program initially, when you maintain the program, when you just read a program, try to understand what it does. We do reasoning all the time. And this reasoning happens for all kinds of programs, not just mission-critical software, but even dancing clowns on web pages. You need to reason about in some way. That is, you need to understand how to think about the programs. And that's a skill that needs developing. And it teaches you how to think about the programs and how to reason in your head about the correctness. Now, of course, if you have tools to do that, you could use the tools as well. But so much of what we do now, and probably will do in the next few years, surely, will be still thinking in our heads about what the software that we're writing. So the question then becomes, how can we teach students to develop those thinking skills? That is, what do you need to understand why a program works or why it might not work? So one area that addresses that is that of program verification. So program verification really sets out to say how you reason about the program in its full detail. And you could think about verifying some properties of a program or all properties of a program. But let me take it from that perspective of, suppose that you were doing program verification as part of an exercise. Well, one way that you could do that is sort of a traditional way, and I think that those universities that still teach about program verification often make use of this technique, which is that you do hand proofs. That is, you teach the students maybe about Hoare logic, maybe weakest preconditions, something like that, and then you send the students home with assignments. They do things on hand, do calculations, and they come back, turn the assignment in, and a week later they get it graded. That's one way to do it. Another way to do it is to make use of interactive proof assistants, like Isabelle or Coq or something like that. Here you can do the proof using the machine, which may be a step forward, because then that means that you're sitting at the machine as you're doing the proof. Maybe you get more used to that. Oh, this is something that you do actually when you sit at the machine and program. But interactive proof assistants are notoriously difficult to learn, and for undergraduates, for example, it's probably not the thing to focus in on. So some number of years ago, a couple of decades ago, there was a movement to start using automatic decision procedures, which are today called SMT solvers, and using them for program analysis in various ways. And so extended static checking is such an area. So in extended static checking, what you try to do is use automatic tools, but you don't prove all of the correctness of the program. That is, you don't prove that, let's say, a sorting routine actually sorts. You just show that it doesn't ever step outside the bounds of the array that it's working on. But an interesting thing is that you can actually push that up, and with the same automatic tools, get more functional correctness. That is, you can attempt to prove more of the functional correctness of a program using those same automatic, or not the same automatic tools, but the same automatic decision procedures. And that's what we're focusing on today. So I'm going to show Daphne and Spec Sharp. Spec Sharp does not quite let you go to proving functional correctness. So it lies a little bit below there. But I'll show you Daphne. OK. So to tell you a little bit about Daphne before I launch into a few demos. Daphne, you can think of it as a C-sharp-like language, Java-like language. It has classes. It has generic classes as well. It does not have subclassing. That was one of the that was not something that I was looking at doing research in at the time, since we had done a lot of looking at subclassing and verification with Spec Sharp. So it has no subclassing. Because it has objects and dynamic references, or dynamically allocated storage, that means that you can do lots of algorithms that deal with dynamic data structures. It has Daphne has sequential control only. So if you want to do concurrent programs, there are other tools you could use. OK, what's special about Daphne that sets it apart from other languages is that it has built-in specification support. So this is like in Eiffel that you have built-in pre- and post-conditions, like in Spec Sharp where you have built-in pre- and post-conditions, or if you use Java, if you use Java and JML, the Java modeling language, you also get the similar effect that you get something like built-in specifications. And they include the typical things like pre- and post-conditions and a number of other standard things. Now, when you write specifications in a program, you want some special support. And there, Daphne offers built-in sets and sequences, inductive data types, things like that are very useful in specifying the programs. And those are built in, and their sets and sequences are value types. So you don't have to go through objects in between. And that seems to make a nice difference when you think about the specifications that you write. And there are ghost variables. There are ghost features that you can introduce in your program, but when you compile the program, they just disappear. So the Daphne compiler just ignores all specifications and all ghost variables because the verifier will have dealt with them beforehand. So you can introduce ghost variables just for the purpose of telling the verifier something. OK, that's enough of an introduction to Daphne. So let me launch into some demos. So what I'm going to do is I'm going to give three demos of Daphne, and I will not assume that you know much about program verification to begin with, but then I'll add a little bit more. Okay, so I'm going to be down here, but maybe you can hear me and see the screen. Okay, so what I'm going to do is I'm going to write a program that is going to compute cubes. So I'll write a method. So what you're seeing here is Daphne, and I'm running it inside Visual Studio. So cubes is going to take an array of integers, and it's going to fill that array with the cubes. So how do I say that? Well, I'll write a post condition. So post condition, I say use the keyword ensures, and I say that for all indices into that array, a sub I is going to be equal to I cubed. That is. So what I've done now is I've specified the intent of the method. So I intend to fill all of those array slots in that way. Well, I need to write some other parts of the specification as well. What you're going to see here is that as I type in the program, it's not just the syntax checker or the type checker that run in the background, but also the verifier. So I'm running the verifier. And here's complaining in the post condition that I may be dereferencing a null pointer. Well, that's of course, because I intend everyone who calls this method to call it with a non-null value. So immediately here, just after writing one little line of specification, we're getting told to write another line of specification that is an important piece that every programmer should think about when they write a program. That is, what are the conditions what are the restrictions on parameters that I expect to be called with? In this case, that the parameter is not null. I'll also have to say that I'm going to modify the elements of the array, so I'll fill that in. Now we get another complaint here too, which is that the post condition does not hold, which should not come as a surprise to anyone since we're not doing anything in the body yet. Okay, so how are we going to solve this problem? Well, we're going to solve it by introducing a loop in the standard way. So I'm going to loop through the indices of the array, and now let me show you right away what how an important point that comes up, which is one of the perhaps a major teaching points to overcome when you use, well, any kind of program reasoning technique. And that is that we can't reason in our head about all of the infinitely many in executions of a loop that you might have. So instead what we do is we use the concept of a loop invariant. So loop invariant is like an inductive hypothesis when you try to prove something in mathematics. And so loop invariant holds at the top of every iteration. What that means is that it holds before the guard is evaluated on every loop iteration. So to demonstrate what that does is, if we think about this program, we would all say, well, after this simple loop, n is going to equal the length of the array. So we can actually write that down as an assertion in the program, just like we're used to dealing with assertions. And in this case, it will flag that as possibly not holding. Now, this is the sort of thing that occurs with loops, because of the way that the program verifier works and the way that the reasoning techniques are set up to work is that you reason through the loop invariant. And in this case, there is no loop invariant stated, and so it doesn't know, all it knows after the loop is that n is no longer strictly less than the length of the array, but it could be equal to it or it could be higher than it, because the reasoning then does not look into the body of the loop to try to figure this out. Now, you can do this in simple cases, that you can run inference to infer properties like this, but when it gets more complicated, you need to understand that you need to provide at the beginning of each loop iteration what properties you expect to hold. So what I'm going to do here is I'll add a loop invariant. In this case, I'll just add it manually. And even though the tool I'm using does infer some pieces of it, let me just write the whole thing to show you what it would look like. And I would say that A ranges between 0 and up to the length of the array. And now you can see that there's no complaint anymore about the assertion at the end. Now it knows that if we ever get out of the loop, the invariant holds just before the loop guard is evaluated, and then if the loop guard does not hold, then there's only one possibility, and that is that n is equal to the length of the array. The tool Daphne also proves termination everywhere, but very often you don't have to tell it anything extra at all, like in this case. It figures that out by itself. But it always proves that things terminate. Okay, I don't need this assertion at the end, so let me delete that. But so then returning to the problem of the cubes. Well, how are we going to compute the cubes? What the postcondition says is that we want this property to hold for all indices I in this entire range. So a common trick to coming up with a loop invariant, or what the strategy of the loop is, that we were going to say something similar. So I'm going to just copy this thing. But instead of saying that every time through the loop that all of these indices satisfy the property, I'm going to say that they satisfy the property up to the first n elements of the array satisfy that property. So this gives us a way to build up the array, and we can do it, and we state that in the invariant. So now in the body of the loop itself, I will just simply set the array element to that. And what I have here now is a program that is verified to be correct. I use the tool, I interact with the tool because I get the red squigglies and I have to interact back and do things. In these cases, I added some loop invariants as a result. But you can see that I don't actually do the logical parts of the proofs. I don't use modus ponens and things like that. That is, all of that is done automatically. And the reasoning about arithmetic and here in this case also is done automatically, and quantifiers and so forth. But let's have a little bit of fun with this example, just to show you how you can proceed with teaching something about loop invariance. So what I'm going to do is just a little somewhat academic exercise, but it's a fun little thing. And that is that we're going to impose on ourselves the restriction that we don't want to use multiplication in the program. Whether or not that's realistic, it doesn't matter, but here's the exercise. So if we don't want to use multiplication in the program, well, how are we going to possibly compute the cubes? Well, one way to do it is that you make a wish, and that's good. So I'm going to wish that I had a variable c that invariantly, that is at all times, every top of the loop iteration were equal to n cubed. Because if I had such a variable, I could just replace that assignment by just setting a sub n to c. Okay? Now you think that's wishful. Well, well, I don't have such a variable. There's no such variable at all, so I will introduce one. And what will I set it to? Well, I should set it to a value such that that invariant holds initially. So what value might that be? 0. Good. All right. You've taken one of these courses. Maybe. All right. So that's good, but I'm not maintaining the loop invariant yet. So one way to maintain it is just to set c at the end of the loop to the value that I wanted to have. But of course, now that would be a correct program, but I'm now using multiplication, and we tried to impose on ourselves that we weren't going to do that. So what you can do is, if you want a particular property, in this case that c is equal to the n cubed, what you can do is you can push that backwards. Now, if you're familiar with weakest preconditions, you know exactly what I'm talking about. But even if you're not, you can just think of, if we want c to equal to n cubed after that assignment, if I substitute for n plus 1, that's what I would want c to be equal to beforehand. So I could have just as well said that what I want beforehand is that. In that case, I can get rid of the assignment afterwards because it's redundant. So this is also a correct program, as the verifier tells us. But I'm still multiplying. Okay, so let's get on with it. Let's see. Well, I remember how to distribute multiplication and addition using Pascal's triangle here. But just to be sure, let me show you what you can do with the program verifier. Is like a big calculator at your disposal. So you can use that calculator to calculate things. For example, I can just have it check for me that this thing is equal to n cubed plus, anyone? 3n squared, thank you, Serdar, plus 3n plus 1. All right, so I can type that into to my program text. And really what I'm doing by adding an assertion is I'm asking the program verifier, do you know that this holds? Just like I asked after the loop before previously, but that is n do you know that n is equal to the length of the array here? And this is correct. So in fact, so then I can just take this part and just stuff it as the right-hand side of this assignment. Of course, I didn't have to do the assert at all. That was just to show you that you can ask questions of the program verifier in that way. So let me just get rid of it. Well, this is a little bit nicer actually now, because here I have n cubed, and I know that invariantly at the beginning of the loop, c is equal to n cubed. So I can replace n cubed here by c. So now we've gotten a little bit closer. I'm still multiplying, but at least I'm not cubing. So this was such a wonderful idea that we make another wish. The new wish is going to be that I have a variable k that is equal to this thing. Let me just move it up there. Because if I had a variable equal to that, I could just use that in the update to c down there. But I don't have such a variable, so I will introduce one. And what should be the initial value of k? 0 and 1, what should it be? 1, okay. So we wanted to establish the invariant to be initially. That is, that we want the invariant to hold upon entry to the loop. N is 0 at that point, so k should be equal to 1. All right? That's good. But I also need to maintain the invariant. So again, I can do something similar here. I could set k to that value after the update of n, then everything would be cool. But I don't want to do that. I want to move it before the update to n. So let me move it up here, and then just replace these by m plus 1, just in the same way that we had done before. N plus 1. All right, there we have it. So again, the program verifier tells us that this is correct. But let's distribute this now. So let's do this. We can do this in our head. N squared plus 2n plus 1. Oops. There we go. And actually, I can distribute that as well, right? So this is going to be 3n squared plus 6n. Am I doing this correctly? Of course, I don't have to take it from the audience. We can see what the program verifier says. But that seems to be good. So, well, that's nice, because look at this. 3n squared, that's what we have over here. 3n, that's what we have here. And 1, that's what we have here. So I can just erase those parts from here. And replace it all by k, because that's what k is to begin with. And 3 plus 3, I can just simplify my program text. So again, we have a correct program. And we're still multiplying, but we're not, now we're just having a single multiplication here. So we can apply the same trick again. And now we know the rules of the game. So this is pretty simple. I'll do that. I'll introduce the m, which should initially be 6, right? And here we can just eyeball it, right? I mean, m, if n goes up by 1 in the iteration loop, m should go up by 6. So that's the program. Now, if you look at just that program. Oh, yeah, thank you. Thank you. There we go. That's the program there. If you just looked at that program, it might not be immediately obvious to you what this program is doing, but we're computing the cubes. And so in this little exercise, I've shown you how to use the loop invariants. And I think that an example like this hammers home that the loop invariant states something that holds at the top of each loop. So if those equalities that I have there hold at the top of each loop, then this program will generate the right result. And again, I can go all the way to, I mean, I have a post condition with a quantifier and everything. OK, that was going to be the end of that demo. I have 2 shorter things to do. But are there questions about this one before I move on? OK. Would you have written this program yourself? Patrick. Oh, Patrick, yeah. The program might overflow. In some, yes, in some languages, all of these arithmetic things may overflow. In Daphne, they won't. Daphne uses mathematical integers, unbounded integers. So if you were doing this in a bounded computer, right? But you have dynamic allocation as well. So I mean, we still have the bounded computer. The bounded recursion as well. And I mean, that is, all recursion is proved to terminate, but I mean, there's no particular bound. So again, I mean, we're dealing with a bounded computer, but what you prove is that, actually, the only thing that Daphne does not prove is that you don't run out of storage. So which is an example of all of those things: infinite or unbounded recursion, or allocating too many things, or having integers that would just be too large to fit in your computer. Those would be problems that Daphne does not check. But if you do this computation in a different language, like let's say in C, where you have bounded integers, the verifier that we have that's similar to this for C programs does check all of those arithmetic operations to make sure that they don't overflow. So that's a really important point. So the way to think about this is that, well, I like having mathematical integers in my programming language. And if you heard Jan Vitek's talk yesterday about dynamic languages and so forth, maybe that's just a way to, I mean, you think of how do you get there quickly with authoring your program. In that case, that's very nice. You don't have to think about those details. But if you go beyond that, I mean, there are tools to do it. Here, the focus is on teaching program verification, that is, teaching about loop invariants. And if you want to include that as well, you could in a different language. OK, was there another question? Sarah, right?
Was going to be my point, this being a session on teaching.
Oh?
This was a lot of fun, but probably it's a good example for the mathematically inclined student. But for the non-believer in program verification, can you think of a way of making loop invariants more digestible or attractive?
Right, so the point is that this is a rather mathematical example. And this, indeed, I think that if you look at textbooks for teaching program verification, what they tend to do is use mathematical examples because we're expected to understand the mathematics that goes behind it, and then we can focus on the programming concepts. But having other examples that are more computer science related would be really great. So let's pick that up in the discussion as well. Okay, let's see. So let me show you. Another couple of things. So here's an example that looks more like a program, like a typical program with a class and some fields and a method. And it's an insert method that actually this insert method is rather silly, but just for demonstration purposes, what it does is it takes a parameter n, and it's going to which is a node, and it's going to insert that immediately following the receiver. So the receiver is self, THIS, and it's going to modify self and n, the fields of self and n, in such a way that in the post state, self.n is equal to the given parameter, and n.next is the old value, that is the value on entry of self.next. So it's going to insert it as the second thing in this list. Okay, but we're getting a complaint here that the post condition might not hold. So let me show you a different tool that we have called the boogie verification debugger, which here is running with the Daphne front end. Let me adjust the font and get it out of the way a little bit. Okay, maybe we can see it now. Okay, so so this looks like a regular debugger, and we can look at values. We can expand and collapse objects and their fields, and we get some concrete example. So this gives you a concrete example of what's going wrong with the verification. Just like when you run the program and it crashes, you get one concrete example of something that exhibits the crash. Okay, so let's take a look here. What we get in this debugger is we get not just one state. Debuggers traditionally have given us just one state, but if you use something like the tracing features in Visual Studio, you can get many different many different states of the program. Here we're getting all of the states of the method, which there are 3 of them. And we can look at then, it says that n.next is equal to null initially, and here it becomes node tick 0, which is just a symbolic name for saying some pointer in the heap that we're giving the name node 0. Okay, well this is a little bit, well actually first of all, we can see that n.next in the post state is equal to node 0, whereas self.next in the initial state here is equal to null. So indeed these two are not equal, but why might that be? Well, if we look at n.next in this example, we can see that it changes between states 1 and 2, which is, in other words, it's changed by that statement there, between state 1 and state 2. That's perhaps a little bit surprising, because this updates self.next, and it's n.next that changes here. Well, why is that? Their alias, right. So if this can only, I mean, n.next could change here only if n and self are the same. And indeed, if we look at this, n is equal to node 0, and so is self. So that's the problem here. So to fix this, what we would do is just say as a precondition that n is not equal to self, and then it verifies it. Now, I mean, this is just a simple example, which is rather unmotivated, I guess, but it shows you the use of the verification debugger. Okay, so let's see, I have just 2 minutes left. Should I launch do one? Okay, I'll do one more. Okay, so let me show you another feature that you can get when you use a program verifier and a language associated with a program verifier that you don't get from just having a programming language. Okay, what I'm going to do is I have here a program that's a little bit similar to the cubes example, but this finds a 0, and it just does a linear search of the program, and all you really need to look at here is that you can see the post condition says that if we return a negative value, there is no 0 in the array, and if we return a non-negative value, then it's an index that has that value. Okay, but suppose that this array that we're given has 2 special properties. Suppose that one of the properties it has is that every index of this array is non-negative. Okay, that's not too hard to believe that could be the case. But here's another property that's a little bit more special. Suppose that for every index I, if I is an index and if I plus 1 is also an index into the array, then it is the case that if you look at a sub I and you're going to compare it to the a sub I plus 1, that it goes down by at most 1. Okay, that's what I'm saying there, right? If you look at a sub I and you subtract off 1, that's a lower bound to a sub I plus 1. So what this is saying is that if you look at the array, the elements of the array, they can go down by at most 1. They could go up by, successive elements could go up by any amount, but down by at most 1. Okay, so if we do that, we can actually write a more efficient program. Anyone? Well, this will be fun. Okay, then, all right. We can do a sublinear program here. Suppose that we're looking at that the array slot a sub n is equal to 7. Well, since the successive elements go down by at most 1, that means that we don't have to look at, the next element we'd have to look at is 7 steps ahead, right? So I can say that like that. But now comes the problem. How do we convince the checker? How do I even convince you that that's correct? How do we convince the verifier that this is correct? So what I'm going to do, which is a little fun trick here, but and of course, since I like programming, it's going to look like programming. So what I'm going to do is I'm going to write an inner loop. And I'm going to start at the inner loop at n. And I'm going to march up to n plus a sub n, just incrementing m as we go along. And what I'd like to say is that as an invariant, we have this property that we only pass things that are non-zero, okay? That's the idea. So, but if I try to do this, I should get some complaints. Semicolon, that's a simple complaint. Okay, I get the complaint that the index is out of range because all it knows is that I is less than m, and here I'm trying to say something about a sub I. So I need to have some more information about n. And that's easy in this case. We can actually say that m is always strictly less than the length of the array. That happens to be true initially because that's the only way that we would enter the outer loop. And we can maintain it inside the loop if I just added an if statement here that says that if m is now equal to the length of the array, we'll just break out of the loop. Okay? That's going to maintain that. But this is not quite good yet because we need to maintain that invariant. That's going to be the crux of it. How do we convince the checker that we're not stepping over zeros? Well, we can do that by writing another invariant about something that is true. We're trying to get to n plus a sub n. And we're currently at position m in the array. So we have some distance to go. That distance to go is equal to n plus a sub n minus m. Now that distance that's yet to travel, that we have to go before we reach that endpoint, that is also lower bound on the array element that we're looking at. So I'll say that that is, a sub m. That's a lower bound of that. So what we're really doing is, here it proves it. What this means is that this is really an inductive proof that we did, just like any loop for that matter. And we're saying we're reasoning one step at a time that latest invariant that I added there holds. So, and of course to do that it needs to use that special property about A that we gave as the precondition. And so this loop proves it, and it proves therefore that when you get to the end of this loop, it knows that whatever m is, when we get to the loop, it's at least that much, and everything to its left is non-zero, so it's okay to assign a sub n here. But now you're asking, how did I improve matters here? Because now we have a more complicated program and an inner loop, and this is no more efficient. Well, I declare that variable to be a ghost. If I declare that variable to be a ghost, that means that when the Daphne compiler gets this, it will just rip that out. It will not compile this into executable code. It will also notice that here's a loop whose guard uses m. That means that the entire loop is a ghost loop. So this loop is not going to be there during execution. So the only purpose of adding that loop is to convince the verifier that the quicker assignment that I did there is correct. And you can do that as code. Yeah, Marianne. Yep.
From a student perspective, like I think writing a loop invariant is very challenging.
Yep.
There's not a lot of guessing. So the fact that tool is helping the process is really great. But I think from a student point of view that they have to do some code transformation, introduce new variables, supporting variables, and change the code itself.
Right.
And especially the first example where you go from n to like introduction of the 3 extra variables, that may not be very intuitive to students.
No, right. So I agree. I mean, working with invariants is, takes some practice. It's a skill that you have to develop. I've written a few of these before. But in this case, first of all, you don't actually change the code. You change the program text, but you don't change the code. That is, the executable code remains the same in this case. That is, with the extra loop. So, because the rest is just Go stuff. So when you introduce the loop and when you reason about these extra variables, right, you have to understand the invariants. But I challenge, anyone to suggest a better way to reason about it. That is the way that we reason about inductive properties in mathematics as well, is that we reason via induction. That is, we can't immediately prove everything, so we build it up one step at a time with an inductive hypothesis. So I think that it is a difficult thing, and I think that it's central to reasoning about programs. And so therefore, it seems like a good skill to learn. So maybe Rajeev and Rosemary have more to say also. Well, you too have in a number of years ago, I know, taught using these tools. So we'll save that for the discussion then. Okay, any other questions here before I return to the slides? Yeah.
For example, generation facility would be good for guessing a loop, finding out that it failed and finding an example. And
right, all sorts of things. We have the masters in the audience of the Cusots of finding invariant. So there are lots of techniques for coming up with invariants that would help. The tool I'm showing here does something very little. It does a little bit of abstract interpretation, but very, very little. So much more can be done. And there's plenty of room, of course, for research as well there. Okay, let me return to the slide deck here. Okay, so I showed you this tool in Visual Studio. You can use this tool and the other ones we'll talk about. You can use it in Visual Studio. You can use it from the command line, or you can use it from this fun website, Rise for Fun, where the others will have more to say about as well. So you can just type in programs there. Let me just say something here. The version of the tool here is slightly out of date, and the person who knows how to get the new version out here will be back in a few days in the office. So if you try it yourself, soon there will be a new version, but you should try it yourself. Okay, so here are some references. You can find these in the slides later. Let me just highlight a couple of things that I didn't talk about. So Rosemary will talk about SpecSharp. VCC is a verifier for C programs, which is similar to what I showed for Daphne, but because it's C, it also handles concurrency and non-safe sorts of things, which means that that it's harder to use the tool because you have to say more things that the language C does not automatically give you. But the tool is available. And finally, Verification Corner is a set of videos that are kind of fun. So I invite you to watch those as well. Okay, so with that, I'm going to pass it over to Rajeev. I'll switch the slides for you, I guess.
Is it on? Now it's on. Okay, thanks, Rustan. So I'll talk about some experience that I've had with using Daphne in teaching a course. So let me explain a little bit of the context. So the course I'm going to describe is a course that I teach occasionally at Caltech. You'll see on the right is a flyer I often put out when the enrollment period is happening. It's called Reasoning About Program Correctness. It's course CS116. I've taught it twice now, once in 2008, once last year, and I'll be teaching it again this year in the fall. It's about 18 lectures. Caltech has a quarter system, about 12 to 13 weeks. So the course covers 18 lectures. Each lecture is about 90 minutes. The audience are typically upper division undergrads and graduate students from various disciplines. So Caltech is a little bit of an unusual place in the sense that it's a small school, but it's a highly selective school, very focused on engineering, very strong students, and typically most of the undergrads at Caltech I would compare very favorably with grad students I have seen at other universities. So the students are also the CS department at Caltech is a bit small, but there are lots of connections with people in EE and control systems. So I have students from I'd say a little bit over 50% are from CS, and then the rest are from EE and control systems. I've even had somebody from biology sit in one of my classes. The students don't have a previous background in formal methods, but they do have background in programming. So one of the requirements for the course is at least they've taken a class on basic algorithms and learned how to do some basic programming. The other thing that's unusual about Caltech are the class sizes. So the class size that I taught in the fall last year was 8 students. And that's actually, while that may seem a bit small to you, that's actually more than what I was expecting when I started teaching. Because class sizes at Caltech are pretty small. It's not unusual to have a class with 3 or 4 students. Again, because it's a small department. So that works a little, the dynamics of teaching to a class of that size are a little bit different, but they work definitely in the instructor's favor, as you can imagine. The course is not required, so this is a good thing because it means that most of the students who are in the class are not there because they're forced to be there. However, it does satisfy a requirement, so it's, and that helps because students who are interested in the topic at least get besides the knowledge of whatever I teach, they're also getting to satisfy a requirement that they need to fulfill as part of their degree. And just the grading that I do, because again, Caltech focuses more on, doesn't focus as much on in-class exams. That's sort of a culture at Caltech. So, and I like that style. So the grading is done on based on 4 take-home assignments. So in this course, in 2008 when I taught it using more or less the same material, which I'll describe in a minute. But using based on hand proofs, as Rustan described, which are kind of tedious and didn't work as well. And then last year I switched to using automatic tools, verification tools, and I used Daphne for about 60% of the class, and then switched to VCC for the last quarter. And I'll talk a little bit about that. So the material that I cover in the course is verifying sequential programs. So the theory is actually obviously very old. It's uses based on Hoare logic. So we start off with discussing how to write specifications using pre and post conditions. We go on to how to the rules of inference of Hoare logic. Then we switch to using the theory of weakest preconditions, describe the correspondence with Hoare logic. We start talking about how to use pre and post weakest preconditions to describe the semantics of a small programming language. We then start playing around with what if we wanted to describe a statement with such semantics, how would we write the weakest precondition equations for that? So that gets people to understand how weakest preconditions can be defined. And then we, somewhere along the class, towards the latter half of the class, we'll talk about how weakest preconditions for loops work. And then we'll go into a little bit of the theory. So we'll talk about fixed point theory and why the equations for weakest preconditions for loops are the way they are. And overall, my philosophy, or the way I like to teach this class is loosely based on Dijkstra's seminal 1976 book, where the idea is that the point of the reasoning about programs is to take problems that you want to solve and try to solve them. And while you're trying to do the solution, you should be able to convince yourself that what you've got is correct. So the way I structure the class is typically we'll start off with a problem description of the problem we want to solve. We'll start discussing, well, here's somebody wants to solve this particular problem. How do we solve it? So we'll come up with an algorithm, or the students will help me come up with an algorithm on the whiteboard, and then we'll start using the tool to convince ourselves that the algorithm is correct. And typically the first guesses have something wrong with them. They're off by 1 error, or sometimes there's some deeper misunderstanding, and then the tool really works very well. And I'll try to illustrate that with an example in a couple of minutes. So just to give an idea of the kinds of things that we cover, so we start off with simple examples like the Euclid's greatest common divisor algorithm. We'll actually tweak it to prove Bezos' identity, if you're familiar with how to do that with GCD. We'll then go to search algorithms, linear search, integer square roots, sum of cubes, the one that Rustan just did. That's one of my favorite examples to do in class. Things like comparing strings, computing exponents in linear time and in log time, sorting, searching, implementing a set library, computing. This is another one of my favorite examples, is computing Fibonacci numbers, both in linear time and in logarithmic time. 2D search, which is if you have a two-dimensional array and you're searching for a value. The idea is that we try to do lots of examples, and the idea is to focus on these particular problems. And very similar to Dijkstra's book, we'll start off with the problem description and then start thinking about how we would solve it algorithmically. So just to give an illustration of a typical lecture that I like to give is, so here's an example. So we're given an array of integers, R, and a property P. And we are told that R contains at least one element satisfying P. And the question is, find an index W such that R of W satisfies P. Now, when you first see this, you think, everybody knows the solution, right? You use linear search. So you start at one end of the array, and you just scan it, looking for the first element that satisfies P, and that's your answer. Well, and linear search is, of course, very common, and everybody uses it. But what if computing P is expensive? So, for instance, here is an example of a P, which is X is a maximum. P of X is the property that X is a maximal element of R, which says basically that all other elements are no larger than X. If you want to do this, then computing the linear search, the naive linear search algorithm is obviously not something you can't just compute P very easily. So there are different ways to do it. Of course, one way is to use auxiliary variables and store the max and then compare it. But there's a nice little neat algorithm called search by elimination, which not that many people seem to be using. And so the idea in search by elimination is, instead of searching the array from one end, you actually have two pointers to the two ends of the array, and you advance them towards each other. And the nice property and the reason search by elimination sort of works in this example for the maximal element is that even if you're looking at one element, you don't know if it's a maximal, but if you're looking at two elements, you can tell if one can be thrown away. And that's why search by elimination works really nicely for an example like this. So we'll describe this idea. So this is roughly the first few minutes of the lecture, or this particular example. And then we'll start off. I'll essentially bring up Daphne like Rustan did on the computer, and then we'll start typing. And then the class will help me build the program. So we'll start by saying, well, here's a property P. And the nice thing about Daphne is we don't have to say what P is. We're just going to describe the general algorithm for search by elimination when you move pointers towards each other. So we'll just say P is some method that returns a value, which is a Boolean. We'll define a property called hasP, which this is all in Daphne, which basically you can read the middle part of the exists, which says that hasP is true with parameters x and y if there's an element between x and y that satisfies P. And then we'll start writing the program. So we'll write the spec for the program. So there's some requires and ensures, and really the ensures at the end says that you return a value, a res, which is between the bounds of the array and satisfies P. And so we'll start writing the program, and now the students are the ones who are helping me write the program. So we'll write a sort of a skeleton. We can guess. We've already talked about the main strategy. We'll have two pointers, low and high. We'll start them at the two ends of the array, and then we'll march them inwards. So the loop is going to look roughly like that. And now the question is, what goes in the blanks in the if condition? And now typically what happens here is that some student will guess or come up with some hypothesis, and we'll try it, and then let Daphne tell us where we are going wrong. And then the students will help work. Actually, the one thing that I've tried that works really well is if somebody makes a suggestion, then I'll ask the rest of the class, does anybody think that's wrong? And if nobody thinks that's wrong, we'll go to Daphne, and often Daphne will find things that the other students haven't seen yet. And so at the end, we end up with, we'll add the loop invariants, and then we'll end up with the right conditions that make this program verify with Daphne. And so you can then take an example like this and then apply it to an instance of a specific problem. So here's something called the celebrity problem, which is basically it's an example of, it's an illustration of the technique of search by elimination. So the celebrity problem is, given a group of n+1 people, we'll say a person P is a celebrity provided everyone knows P, but P doesn't know anyone. That's typically how celebrities are. So given such that there's a group of such people, and given that there is at least one, there is a celebrity in the group, our goal is to find the index, if you think of it as an array. And so then you apply search by elimination, and you end up with a program that looks very similar to the algorithm that we just presented. So we have we start off with a method that says we're given a relation knows between people, and then we'll define the notion of what is a celebrity, and then we'll write the program, which looks more or less, as you can see, we have these pointers A and B, which we start at the two ends of the array, and then they march towards each other. And at the end, we end up with the index of the celebrity. My experience of after teaching this class is there's lots of things that have really been improved by using an automatic verification tool like Daphne. And I'm mentioning Daphne because that's what we are discussing today, though I do also focus on VCC at the end, as I mentioned. And I think one of the reasons that Daphne works really well is possibly the way I like to teach the course, which is focused mostly on on programming examples. And so the focus is not so much the theory. The idea is that we focus on the examples and then bring in the theory as we need it in order to help us prove the correctness of the algorithms that we're coming up with. So the idea is you have a problem statement, and then you have to invent the algorithm and then prove it correct at the same time. So in this context, I think Daphne works really well for the reasons I mentioned, because of the interactivity and then the feedback you get from Daphne as you're writing your code. The thing that I found, having taught this course both with and without Daphne, is that having Daphne really helps get the students much more involved. The previous experience, as I mentioned, I was using proofs with pen and paper, which really wasn't such a big hit. What I found interestingly is that students really do get very involved with Daphne and really work, sometimes go to great lengths to make sure that their programs don't come up with any errors. And I'll illustrate the take-home assignments that I'll show you an example of that at the end. Daphne is great for explaining programming by using design by contract, because the underlying engine is modular. You have to use pre and post conditions. So every method that you write, you have to write a spec for, which actually works in favor of teaching design by contract. The other thing that I found is that because Daphne and VCC are so similar when you use them, Daphne is a great stepping stone towards VCC. But Daphne has unbounded integers, which is actually good. It's a feature because in the beginning you don't want to worry about things like overflows and so on. But then at the end of the class, I do want the students to feel like they're walking away knowing how to take a real C program, or quote unquote real program that they have been writing real implementations with. And so then they can, once we've studied Daphne for 2/3 of the semester, then switching to VCC actually is much quicker. Another feature as an educator is that grading becomes a lot easier with Daphne, since students are submitting programs that are already, at least Daphne verifies, though occasionally they will put in assumptions or put in conditions that are inconsistent, but those are easy to check. And halfway through my course last year, the Rise for Fun website became active, and that was also works really well because students then don't have to install Daphne on their laptops, which doesn't always work since the compute power isn't there. A few things that could be improved. One of them is that Daphne is a cutting-edge tool, and so there are still things that are changing halfway through my semester. Which the syntax for how to write the length of an array changed, and there was a minor hiccup with that. The thing that I did find missing was that there weren't at the time tutorials or wiki available. VCC has a really great wiki, which also is a bit out of date now. But having such a wiki for something like Daphne would really help, because students could then go there instead of having to ask me or my TA. And the one thing that people have already mentioned is that loop invariants are difficult for students, and they are actually difficult in general. And one of the things that I found that was that in the beginning, students had a lot of difficulty writing loop invariants. They would not understand why Daphne is not able to prove some very obvious property of their program. And then I spent a lecture describing how Daphne translates loops. So at that time, we had already looked at things like havoc and assume statements. We had already studied them, so people knew what those were. And then using those, I was able to show them how Daphne takes a loop on their program, an annotated loop, and converts it into a property that is checking. And after that, things got a lot better. Once they really understood the idea that everything is in the loop invariant, that everything else is havoced, it became really, things got a lot more got smoother. And then the one thing that would also help is there is a way to run Daphne programs, to take some Daphne programs that are executable and actually run them. And that might actually also, I think, would help. We didn't do that in my course. So it was interesting that students were actually writing programs in a language and submitting assignments programs that they could not run. That I think would have helped them, especially at least in the first half of the class. So just an example, I'll quickly wrap up. Just a quick, so here are a couple of homework problems I've given. I consider these successful if I've had at least 2 or 3 students out of 8 get them right, and that's always been the case so far. So here's one. You're given an array of size n, and you're given the property that the first element is strictly less than the last element. And you're supposed to write a Daphne program to find an index k such that a of k is strictly less than a of k plus 1. And the interesting twist is that the running time of the program has to be logarithmic. Basically, I just give them the spec so that we're all talking using the same variables. And then they're supposed to write the body of the method and prove it correct and submit then a solution. And then here's a slightly more complicated one. You can look it up. I sort of tweaked it because I work at JPL. So there's a circular space station, and there's an astronaut there's oxygen tanks at various locations, and the astronaut has to float around a circuit, making sure that they always have oxygen. And you're given a certain property, and you're supposed to find a starting location from where this astronaut never runs out of oxygen. And this actually was probably the most challenging problem I gave. This was on the final assignment. And actually, at least 2 students got it right. So I thought that was really great. Okay, and so I'll stop. If there are any questions, I'll take them now, or we can continue the discussion at the end.
Okay, so I'm teaching in Ireland, and I wanted to share my experience of teaching undergraduates and master's students program verification, and in particular Spec Sharp. So I suppose to start off, I want to set the context, and just to say that the degree structures are quite structured in that, I suppose in 1999, we had a European pledge to try to put all our degrees into some format so that we could easily transfer students between courses, and that courses were transparent. So that typically undergraduate degree programs are 3 years and a master's program is 2. So it's a 2-year taught master's. And that with every year that you have 60 credits, it's a European credit transfer system, so ECTS. So we always talk about credit systems, 60 credits per year, and a course is typically worth 5 credits. So a 5-credit course would typically be 24 lectures, plus lab work, plus independent study. And there's a formula to follow to say what the weighting is. So I say typically 3 plus 2, so 3 years undergraduate and 2 postgraduate, but in some cases it ends up being a 4 plus 1, so a 4-year honors degree program, and then 1 year to top up to get the master's. Okay, so that's just to give you some background on the structure. There are 2 courses that I teach at NUI Maynooth, which involve program verification. And one is at an undergraduate level. So this is 357, software verification. And this is just taken from the course calendar, the description of the course. What it is that we expect students to know at the end of the course, so the things that they should be familiar with. Okay, so we talk about testing. These are undergraduate students. They've done year 1, year 2. That's 60 credits per year. So 12 courses per year typically. These students have probably come back from a work placement. They've done 6 months work placement, and they come back and we talk about testing, we talk about verification, and correctness of software and program specification. Okay, so as I said, that's 24 lecture hours, 24 lab hours, and then 32 tutorial or independent study hours, which are quite impossible to measure, but that's what we tell the students that they should be doing. The course is delivered over 12 weeks, so typically 2 lectures per week, 2 labs per week. Okay, the second course that I'm going to talk to you about is a master's level course. So this is 7.5 credits, so it's a little bit unusual, but it's also delivered in a different manner. It's delivered as a 2-week block. So the students come in for 2 weeks, and in week 1 they have lectures from 9 to 5, Monday to Friday, all on rigorous software process. Okay, so during that week we cover lots of different tools, and I spend probably 1 day of that week dealing with Spec Sharp and related problems. Okay, the second week of the course is where they do project work or marked assignments, which goes towards their continuous assessment. So these courses are typically, for undergraduate and postgraduate, 40% continuous assessment and 60% for the exam. Although with this one, I tend to try and make it 50-50. So there's a focus on continuous assessment. Okay, the topics are similar, but these students, they're master's students. We go into topics in a little bit more depth. Okay, so just again to talk to you about the type of students, like Rajeev is in a nice position where the course is not required, so the students he gets are students who want to do that course. The students I get have to do the course, okay? They have no choice. So the degree students, they have to have passed first year and second year. You can't go into third year unless you've got through your 2 years. So there's no mixing and matching of modules. You must have passed those. Typical background, object-oriented programming. Typically, they've done Java. They have done some UML. They have taken their algorithms and data structures courses, done something on software metrics, testing, and they've probably taken a course in first order that involves first order logic somewhere along the way. So we require them to take maths courses as they go along. Okay, and as I said, the course is compulsory in year 3. The MSc students can come from any degree program because we're talking about transferring students between different courses and different countries. They can come from any program, so they don't necessarily have this undergraduate course as a background. And again, it's compulsory. They must achieve at least 50% in this course in order to progress in their masters. Okay, so just a little bit about where we go from here. When I get the students in, they've done no program verification. They, as I say, might know a little bit about first order logic. When I get them at the beginning, we talk about specification, might do some OCL with them to build on their UML. We talk about Hoare logic, and we typically do work with pen and paper or at the board and talk about post conditions. So, you know, you've got a post condition which says that you're going to sum the elements in this array B, and we say, well, how are you going to use that to derive a program? So what are the stages that we do, or what are the rules that we apply in order to calculate what's true at each point of the program, and to figure out what we should write down in our loop body, or what we should write down to initialize our variables and make sure that's correct. Okay, and it gets more complicated as we do the derivation, but there's very strict rules using Hoare logic, using Lucas precondition calculus to calculate at each stage what should be true. Okay, so typically this is done on pen and paper, or was traditionally done on pen and paper. I taught this course, I think I'm teaching this course since 2005, and in 2007 I switched to using tools. So I still introduce Hoare logic with pen and paper, and we work through problems. But then we introduce the tools and show them how they can use the tools, and I'll talk to you about that in a moment. Teaching the course using, before using automated tools had a lot of problems. Limited tool support. So when I started teaching the course, I was teaching specification languages like Z. It was heavy on the syntax. Students got very frustrated with not even writing the formula down correctly. And when they wrote it down correctly, they didn't know if they were specifying correctly or not. They were coming to me or the teaching assistants, and it was taking time to work through this, to tell them and to explain to them what was wrong with their specs. Then we looked at some tool support, and we found that there was limited automation. So we used theorem provers, we used Coq, we used Isabelle, and again, we had support from the tool, but students were sitting in front of the machine going, oh, I don't know what to do next. There's so much notation, I don't know when I'm writing something that's correct. So the mathematics up front intimidates quite a few students. The good students, the strong students, they're okay. But the majority of the students in the class are struggling and intimidated by I suppose even the symbols that are used and what it is that we're trying to do. Plus they just don't know when they've got it right. The other problem I found is that by using tools that they were changing all the time. So one year I'd start and I'd work with a tool, and the next year I'd go to use the tool and it had changed hugely. Okay? Now one of the tools I used was the tools associated with JML, for example, so the Java modeling language, and that was working really well. But there's so many different versions of tools and so many different versions of the languages that the students found themselves working on one version in the lab and going home and downloading something else, and it wouldn't work there, and it just led to confusion. With all of these things, feedback to the students was lacking. They were depending on me or the teaching assistants to give them feedback because the tools weren't good enough. Correcting homework was time-consuming. Okay, so it took a long time to work through this, particularly if it was handwritten. Really, really, really difficult to work through. Huge problem. View-motivated tutors. I found it impossible to get somebody who wanted to be the teaching assistant on my course. Okay, so this said to me, something's really wrong. Okay, they're postgraduate students, they're looking for extra money by doing a little bit of tutoring either privately with the students or as teaching assistants on a course. And no, I don't want to teach that course. Okay, so they found it difficult. And I just felt that students' effort and their enthusiasm was completely drained on the wrong thing. They would come to you and they would have problems, but they weren't thinking about specification. They weren't thinking about verification. It was, how can I get this tool to work? Why does that not make sense to the tool? And it was quite frustrating. So when I started working with the SpecSharp programming system, I suppose I was looking for something to fix all these problems. And I came across the SpecSharp programming system and started using it. So SpecSharp is very like Daphne. Daphne focuses on full functional correctness. SpecSharp is built on top of C#. So you've got access to you're using the C# libraries. It's got the SpecSharp programming language, which is basically C# with contracts added, preconditions, postconditions, and invariants. We've got the compiler, and then the back end is the same as in Daphne. It's the Boogie verifier with Z3 for theorem proving. Okay, so the nice thing is that the students write their SpecSharp program. They just press a button, and they get back either a list of errors to say that their program hasn't verified, or they get a correct program. So you saw with Rustan using Daphne through the Visual Studio environment, and we can do the same with SpecSharp. And students like it because they just write their program and they get immediate feedback in terms of these little squiggles that appear under the errors. Okay, so Visual Studio was the first way that I started using the tool, and students were really excited because they could get immediate feedback when they typed something. You can use SpecSharp with the command line, and that appeals to certain students, and not all, not the majority, but you can use it at the command line if you wish. And option 3, which both Rustan and Rajeev mentioned, using the Rise for Fun, and I've used that as well. The major advantage is no tool installation necessary, so it's portable and easy for students to, no excuses basically, okay? So that students can get access to it. So in class, what I typically do is I use the Rise for Fun website quite a bit. I present the students either with a specification and get them to write the code, or sometimes I present them with the code and ask them to write the spec. But I put these samples up on the Rise for Fun website, and students can interact directly, just typing in the requires clauses where they write their precondition, modifies, what it is the method is allowed to modify, the ensures clause, what is it that must be established or will be established by the program. So we put up these on the Rise for Fun website and interactively work through these with the students in the class. And I generally have another URL up there where they can find the solution. So they can go back in their own time, they can go back to this, they can play with it, they can interact, they can see the result, and then they've got the solution. What they see if they're using Rise for Fun is this in a web browser. So they type in their program just here. Okay, there's no fancy syntax, but it's just a simple program that they're typing up. They can get direct access to the tools and immediate feedback. Okay, so back to the courses that I'm teaching. The undergraduate one, I focus mainly on writing method, preconditions, postconditions, and loop invariants, and use of the spec sharp system. So out of that course of 24 lectures, I probably get about 6 or 7, which allow me to cover spec sharp. So that's 6 or 7 hours. In the rigorous software process, as I say, I have a day or a day and a half, and I talk about method contracts, but I also cover things like inheritance and ownership and aggregation. So the students get to see specifications for classes where we've got objects that are going to interact. And we talk about the back end. Okay, so at the beginning we talk about writing the specifications and verifying them, but then students do get curious to know how this works. And we talk about how the spec sharp programs are translated to Boogie, and the Boogie programs are verified. I've also used it in a summer school which we run every year for undergraduate students, and these are just second-year students, and they come from various places throughout the world. So we don't really know too much about their background, and we find that they get on well, but just using the interface and writing specs and verifying. And I've also used it in a course in Nancy on an Erasmus teaching exchange, and there the students were from a very mathematical background. And the response I got from them was, oh, why didn't we do this first before we did all the theorems and all the logic? It would have made so much more sense to understand the context that we were doing our reasoning and logic. In terms of assignments for students, the first year I was very ambitious, and I gave them a big project that was not well specified, and I said, go ahead and specify this and write some code, and it was a nightmare to mark. Okay? So I give them the university marks and standards, which basically it's all the sets of rules that describes the courses and tells you how you can progress from year 1 to year 2 and so on. And the students had fun because they found a loophole in the rules for the university system and how they could progress. So at least they learned something. But it was a nightmare for me to mark because they couldn't break the problem down into its modular components and specify it well. Things like card games worked well. The students had fun. Again, I needed to be very careful about how I specified things and then get them to write the code and verify that their code was correct. Other things like Rajeev, Dijkstrom Fane, textbook, examples out of that are good for short assignments. Verification benchmarks like those from the VSTTE conference. There was a paper in 2008 which set out a set of benchmarks, and they were specifying queues and sorting algorithms, searching algorithms, those type of things. We had a competition at VSTTE last year, which Peter was involved in and Gary, and some of the problems from that proved to be good exercises for the students as well. And some more benchmarks that were suggested, which I've got the students to do 1 or 2 of them, but we use those as future assignments. So just to wrap up, what worked, what didn't work? What worked, the students were really motivated by using the tool. They were getting immediate feedback, and what was really nice was that after a while, the students started to ask, how does the tool work? So previously, we were doing everything with pen and paper. We were working with tools where they were focusing on the syntax, and they were focusing on what it is they should be writing down so that the tool was happy, not so that their program was correct. Whereas here they were getting feedback quickly and they were motivated to learn how the tool worked. And I found that was one of the really nice results. Students were using the tools outside their coursework, so I got a knock on my door to say, you know, I want to talk to you about program verification. And I looked at the student going, who are you? And they, oh, I took your course last year and I'm doing this project and I'm using the tools and I'm getting this error and I want some help, or I need to know how to express something. So that was really good. Students were also motivated by the fact that they were using a real programming language. They were using C#, okay? So they liked the idea that this was built on top of C#, and it was something they could put on their CV. Well-defined exercises, okay, you really do need to have those exercises well-defined, otherwise the students are going to back themselves into a corner and get frustrated, so a bit of organization does help. They liked the immediate feedback in Visual Studio, and the Rise for Fun website proved to make things very easy in terms of portability and transfer. Things that didn't work, I think we've already heard about loop invariants here a few times. Yes, it's a problem, and when students try to write loop invariants without thinking about the verifier works, then they do find it difficult. Learning to debug programs by interacting with the verifier the way Rustan did with Daphne, writing his asserts and his assumes, and writing in that ghost code, that type of thing students do find difficult, and understanding the error messages. Okay, I think I'm running out of time, but just to say that we've given quite a few conference tutorials, and the feedback there from educators and researchers is that they're interested in using the tools, and the main reaction was, oh, it makes it look also easy. Other observations, I think I've said these already, but generally motivation was increased, students were doing better in their exams, and they're more interested in verification. I find more people are coming to ask about projects involving program verification as a result of using tools, and them not seeing that barrier that was there before where they couldn't express themselves because the notation was too heavy and too hard to work with. Okay, there'll be lots of URLs there in the notes for you to, or the slides for you to see, some teaching resources and some benchmarks. And I'm going to leave you with a few things to think about and discuss with us. So some discussion points, and I'll hand back to Rustan at that point.
All right. So what you've seen is demo of one of the tools, the Daphne tool, and heard from two people with experience. So what we thought we'd do for the remaining time, we have about 11 minutes left, is open up the floor. Something that we would love to see is that when people are interested in doing something like this, there's a bunch of course material and experiences that could be shared, it seems. And a number of people in the room have such experiences. And so we'd love to figure out how to share that best. So here are some questions to think about. So let's see. Well, let me start by, I start right there, I think. Right. Let's see, and there will be a mic coming your way.
Thank you. I don't teach verification, but I do teach software testing. And one of the things we have found that works well is, as part of the testing, to teach the testing principles, is to have the students break each other's programs, right? So what I find here in both the tools from both Daphne and Spec is that the specification and the program are very tightly coupled, right? So is there any work on kind of trying to decouple them, so that, so that we can have them separate? I mean, this is purely a tool support issue, right? Saying that, so I have a specification file, which is stored separately from the program file, so that we can have them tested independently, worked independently, and so on. Is there any work going on that, or are there any other tools?
Want to write, or Rajeev?
So, for instance, in VCC is just uses C, right? So, and C you can write .h files or header files, so you can put your specs in the header files if it makes it easier for you. since you're bound to include them anyway. I mean, that's so you could do things like that. So far I've not found that to be a real issue, because where the signature of the method is, if the spec starts getting complicated, especially in Daphne, I end up defining auxiliary functions that make it easier to write the spec.
But the thing is, the program that we write is intimately aware of the spec, right? So I'm saying there's a way to decouple them somewhere. So, for example, right, so when they start this kind of a course, so they have already written programs earlier, right? So when they start taking a course like this, they had already written some programs. So what might be nice is you say that, okay, so this is the program that somebody has written. Now try to figure out whether this is correct or not. Just break it or whatever.
Right. So what I did in these demos was to write the program and the specifications hand in hand. Yeah. And the way that Rajeev also showed how he goes through solving the problems, it also goes in the same direction. It's much easier to design a program if you design it with the specifications in mind to begin with. Given a program that you try to come up with the specifications afterwards is typically quite difficult.
True.
Mike?
That's what I'm saying. For mixing, if you want to have that capability of mixing and matching specifications and programs in Spec Sharp, you can specify the contracts on the interfaces, and then every implementation of that interface has to live up to that specification.
And that's one thing that I did in my class. I got the students to specify and then to pass their specification to another student and write the implementation, which was interesting.
So I have a question about so for the instructors who taught this course, verification course using tool, how did you balance between pen and paper based inductive proof and actually using automated tool? So my question is, did you actually go through how to do this by hand and teaching them first and then they use a tool, or they just start using the tool and they're understanding how these variants that you provide, the tool does inductive proof.
So I suppose I've used both approaches with the undergraduates.
What is the effective way of teaching this?
I think it depends on the class, basically. If you have students who are not strong on the mathematics and you show them the tools first and get them working with specifications and verifications and get their curiosity up, that's the best way to motivate them. And then you start explaining how it works at the back end. For the stronger students, I've done the pen and paper stuff first, so the master students, and then shown them the tools, and they go, oh, wow, this is great, so they really see that this is simplifying things. But ideally, I still do both, but just depending on your class, use the tools as a vehicle to either motivate them or to make them see how this can be made simpler.
This is a question to Rosemary. The graduate course you taught was, and you said you used 6 tools, I believe. Were they all verification tools, or?
So the tools that we were using were, we used Event B, so in Rodan. We used, we used JML, we used Spec Sharp. At various different stages of the course, we used Lotus and some of the tools associated with that. So, and then some theorem provers, but not all in the one course. Over different years, we use different tools. So.
Well, the question I was trying to get to is for the student who's not verification-minded, who's going to go work in industry, and supposing that my goal is to make him more aware of correctness, have him think about specifications. Do you think tools are easy enough to use at this point to convert such students, or at this point, are we limited to advanced 8-person Caltech classes, or?
Well, I suppose I found that students were, as I say, more motivated because they were using C# for starts, and they thought, oh, this is something I can talk about in an interview, and they seemed to, maybe it was the way I delivered it, but they seemed to think that Spec Sharp was an integral part of this, and that it was something that they would talk about in their interviews or with companies. They're the less motivated students, I suppose, who I did see them using it when it came to code. So I think the tools are at a stage where it can motivate people. I think Rajeev have you taught for industry, or actually no, you've taught a course for industry.
A number of people have.
Yeah.
So Gary, did you have
Yeah, Rajeev, I was wondering, when you give students a complexity bound on a solution, do they verify that using the tools, or is that done just by hand?
So typically, we haven't done that using the tool, though of course you can. You can add appropriate additional assertions and invariants. So no, so typically you just look. I mean, usually these things are, I mean, most of my courses, it's been taking a linear algorithm and coming up with a logarithmic one. I think that's been, for the most part, what we've tried to do, and that's usually pretty easy to tell. So no, we haven't done the complexity bound checks.
Yeah, question over there?
Speaking of industry, nobody mentions secure development. Do you think this is a good part to teach this, or how do you address this?
Well, there are many parts of security. One thing that's meant by security in the last, 12 years is just correctness, right? That you don't step outside bounds of arrays. So that you certainly get from this. If you think about there are many other aspects of security, but so if you, to the extent that you have to reason about the code, then teaching that might be something that that you get an understanding from the tools like invariants, things like that, preconditions. What do they mean? But other things like secure information flow, let's say, you don't get from these sorts of tools.
Things like buffer overruns. So,
buffer overruns
specifically.
Buffer overruns you get all the time, right? Because the program would not be correct otherwise. That you get for the C tools and all of those.
Okay, so not explicitly, you don't see. Okay.
Right, it's just part of the correctness.
Okay.
Let's see, Dave first.
So I just want to appeal to people to share their examples apropos this last point. Because we've got these beautiful sort of Dijkstra, Kaldewey, fan era examples, which are very well crafted to teach the basic ideas, work very smoothly. But we're crafted to have nice loop invariants and to be sort of amenable to do the predicate calculations, right? Well, now you can sort of forget the predicate calculations. The prover needs to do that. So we could hopefully find more compelling examples, less numeric, things like take a list of MIDI events and compress their amplitude range and things like this, right, that are going to be more appealing. Now we need these to go through the prover well, right? So people who've taken the time to devise an interesting example and then tweak the specs and so forth till you get it to actually work with the tool, this would be, this is really valuable to share.
Right, yes, that'd be great. Let's see, so we'd like to see that. Peter.
So I'm, of course, all in favor of automatic program verifiers, but I have some doubts whether automatic verifiers help in teaching verification. It seems a little bit to me like using a calculator to teach somebody how to do multiplication. And when I look at the demos and examples, my feeling is that students will learn how to write specifications and will definitely learn how to write loop invariants. But what do they learn about verification beyond that? Wouldn't they learn a lot more by, for instance, adding a new language feature to the source language and learning how to encode that in the prover? How to reflect the semantics of the statement in the prover, stuff like that. So is it really that you teach verification with these tools, or do you teach specification?
Good point.
Good question. I think for the undergraduates you teach specification, but it depends on, I suppose, there's always the battle of how much verification you're going to be, that's going to be permitted in your curriculum. And I find that we're very tight on the amount that we can. So it would be really nice to have another course where we taught verification, real verification. With the master's course, I find that I have more time to teach them verification. Tools just motivate them to learn about, or to see what it is that can be done, and they're curious about how it works. And we do look at the theorem proving side of things. But yeah, I think with more time, there's a lot of development that could be done there to teach them real verification.
Right, great. So we're sort of running out of time, but let me add one more thing to that, and that is that for teaching specification, you don't, the tools that we've shown here are verification tools that actually do the proofs for you statically. But there's a lot that could be gained from just using specifications for dynamic checking. And for that, the JML has a nice tool suite. Mike Barnett is working on code contracts, which you've seen here as well. Runtime checking at CMU. I have an intern, Jason Koenig, who went through a class last year when they changed their curriculum to use specifications in C-like programs. And all of that, there you learn how to use the specifications and run and get the dynamic checks. So getting dynamic checks for programs, that is checking contracts, pre and post condition, let's say, dynamically is much easier because you don't need to think of the inductive parts of the invariants and so forth. You can just write down some properties and you get immediate feedback. So that's certainly something one can do as well. You can do it with Spec Sharp, and in Daphne you get no runtime checks since it proves everything. But let's see. So we'd love to continue that discussion, but we should end right here to go into the coffee break. So let's give a hand to the other speakers as well. Thanks.